In the second part, we are going to talk about the principles of fMRI. So now we know the basic physiology behind the neurovascular coupling, and now we'd like to know how can we use fMRI to probe or to measure the vascular response. So first of all, I believe most of you do not have the background of the knowledge about the MRI, but actually magnetic resonance imaging, so-called MRI, is kind of the knowledge that you can take 2-semester class in this university. So if you are really want to know the details about the MRI, there's also the online teaching materials in my website. So you can just go to my website and find out the teaching material. There's two courses we call MRI and also MRM, magnetic resonance in medicine. Actually, they are just 2 semesters course right there. But today we don't have that much time, so I try to give you some general idea about the what is the MRI. So first of all, there is a very great video on the YouTube. This is actually, I think, produced by the non-field, health organization or something. And actually, this kind of video is originally produced for kids, for people that they just want them become not scared about MRI so they can take the examination. But I think it is a very good material for people like you if you don't have any MRI idea in your mind. So I think we can take, I think it's just several minutes right there. It's more like a cartoon or something. Just take a look, okay?
An MRI scan looks deep inside your body to produce detailed images. But how does it work? MRI, or magnetic resonance imaging, uses magnets, really strong ones. Magnetic fields are measured in Teslas, and a typical MRI scanner produces 1.5 Teslas, more than enough to pick up your average car. But it also has an interesting effect on the particles in your body. The human body is made up of all sorts of things, including fat, protein, and other stuff like minerals. But most of it, around 70%, is water. These water molecules sit around in nearly all parts of your body, and under normal conditions, they float around happy and carefree. The atomic structure of water includes 2 hydrogen atoms and 1 oxygen atom, hence the H2O, and it's the hydrogen nuclei or protons that are important. Just like the Earth, each proton spins on an axis, giving it what's called a magnetic moment, basically a north and south pole. This makes every water molecule in your body a tiny magnet, and there are billions and billions of them. When exposed to a large magnetic field, the molecules line up and spin at a particular frequency. A secondary magnetic field turns the molecules to face new directions, and when it's switched off, the molecules begin to realign. As they do, the frequency changes, and that's what allows the MRI scanner to peek inside your body. Detector coils placed over your body work like cameras to take pictures of the changes in the magnetic fields. And since they behave differently in different tissue, it produces amazingly detailed images of soft tissue, bone, and organs like the brain. While all of this goes on at a subatomic level, you feel absolutely nothing, and there are no known side effects. See? Nothing to worry about.
So as I said, this is a video produced for the patients that who is going to have this kind of MRI examination. So this just try to give them a general idea and not worry about this kind of examination. You don't need to really worry about. You know, people tends to worry about something that unknown to them. So this kind of the video just try to give them the general idea. If you want to see this afterward, you can just go to the YouTube or just click the link on the handout. Okay. So let me put the principle of MRI in more scientific way or more academic way right here. So actually, we can separate the process of the fMRI into several different steps. As you heard in the video, that actually in our body, there are so many protons. For example, the hydrogen nuclei. Actually, this kind of the particle with charge, with one positive charge, actually will naturally spin continuous spinning in your body. And this kind of the particle with charge, with this kind of spinning property, will actually produce a very small magnetic field. And the direction is actually following the right-hand rule. Actually, the spinning direction is right here. Then you will generate the magnetic field from the some direction right here. However, in your body, this kind of the small magnetic field or vector is actually aligned randomly distributed. So actually, there is no net magnetic field because all the magnetic vector cancel out with each other because different directions. But once you send patient into the MRI room, we always know that the MRI room is kind of a place that it has a very, very strong magnetic field. The magnetic field unit is actually in Tesla. Tesla is so strong that it is over 10,000 times compared to the Earth's magnetic. It's pretty large one, pretty huge one. In this kind of environment, actually, all these small magnetic field will line up, or we call alignment. It will actually align to the main magnetic field. Main magnetic field is the very strong magnetic field that's generated by the magnet of MRI. Okay, so normally this field is around 1.5 Tesla to 3 Tesla. For the brain study, for the fMRI study, I think 3 Tesla is a much better strength for the brain function study. So once you send a human into this kind of 3 Tesla environment, all the protons, all the spinning protons will line up. And as you can see right here, if you see very carefully, actually the direction of the alignment may goes up, or we say parallel to this B0, the main magnetic field. And parts of them may anti-parallel, actually just point to the anti-direction to this B0. But with the summation of all the direction, actually the parallel one, I mean the direction along with the B0 will has a small value. In a small value, just have more protons actually line up or parallel to the B0. So the net magnetic field, we call the NMV, net magnetic vector, will actually follow the direction of the B0. That means parallel to it. However, there is another phenomenon we call the precession. Actually, this net magnetic vector, NMV, is not simply just line up along the B0. Actually, it will just continuously have this kind of circular motion we call the precession. It just circle around with using the B0 as the main axis. It will just precess around this vector right here. And this precession phenomenon is so important that this is the origin and why we can measure the signal in our coil. Actual coil can only record the current. However, if the magnetic field is continuously changing its direction, the dynamic magnetic can cause the current. If you only have a static or fixed magnetic field, there is no current will be induced. It's kind of the Faraday law that the dynamic magnetic field can generate the current. Okay, so precession is so important. Okay, but if you really want to observe these protons or these spinning protons in your body, you need to give some kind of excitation. Just like if you want to know the personality of someone, just punch on his face. If he's so angry that he just want to punch back to you, that means he's people, just with a very bad temper, a very angry one. So don't piss him off. But if you punch on someone's face, he say, "Oh, what's wrong? Are you okay?" Then he's a very good person. So no worry, just punch him again. He won't be angry to you. Just keep asking, "Are you okay right now?" So sometimes if we really want to know something or observe or investigate something, we need to give some excitation, okay, or extra stimulus. And this is actually accomplished by giving an extra radio frequency. We call it RF pulse. This is just another magnetic field or electromagnetic wave. Okay, we try to use this RF pulse to transfer the energy from this wave to the NMV. So in this plot, you can see the NMV originally presets with this V0, but once this NMV obtains the energy from this RF pulse, it will just comes down. And we can use the degree or specific the flip angle. It's a specific term to describe the change of the angle. We call flip angle. You can see the flip angle, if the flip angle becomes larger, that means the energy obtained from the RF pulse is larger. Okay, so you can see the NMV will come to this state. So actually, you can imagine that the original state right here is so-called low energy or baseline state. So it is in it's in a very steady state. But once the NMV obtains the energy from the RF pulse, it comes to the excitation state. Okay. So once the RF pulse is closed, there's no more excitation. Then follow the nature properties. This high energy NMV will try to go back to this original state, right? During this process, the energy will again be released from the NMV back into the surrounding tissue. Okay. And now, during this process, you can observe actually different tissue may have different kind of the property we call relaxation. That means the ability to go back to the low energy or stable state. This is called relaxation. Okay, from the excitation, go back to the baseline stage. Okay. This relaxation ability or the time to finish the recovery or relaxation is pretty different between tissue and tissues. So you can see the muscle may have a specific relaxation ability, but for water or for the fat in your body, maybe another value. So actually, after excitation, we will try to measure the difference, the signal difference caused by the different value of the relaxation, actually. So now you can know that based on so-called T1 and T2 relaxation ability, we can see the signal difference. But actually, if you really want to acquire an image, you need a way to encoding the spatial information. You have the difference we call contrast between tissues not good enough. We further need the information about the spatial encoding. Okay. That's how we acquire the image. So actually, an imaging is composed of contrast and spatial information. Combine these two things, we can have an MRI on hand. Okay. And I have to say, I'm sorry that I cannot spend more time to introduce the general idea or full picture about the MRI. If you want to know more, please go to my website and just see the online video with the materials. But now I'm going to go to the next step. I'm going to introduce how we can use the MRI to probe the vascular response, or how can we probe the oxygenation level changed in our brain, of course during the brain activation. So now let me show you the several terms right here. The first one is the BOD. I keep talking about this term, BOD. Actually, this is the blood oxygenation level dependent. Okay, it represents these four words actually. So you can see fMRI is actually measuring the blood oxygenation level, not directly measure the blood flow or not the neural activity, but actually measure the blood oxygenation level. But as you know before that oxygenation level definitely can change if the CVF flow or cerebral blood flow increased. If the blood flow increased, definitely more oxygen comes into your brain. But also the oxygenation level depends on the brain activation, because once the brain activation happens, the oxygen consumption will increase. So these two things will give you a net number of the oxygenation level. And as we mentioned before, that actually during the brain activation, the blood oxygenation level should increase, okay, to compensate the demands of the energy. So the bold contrast, when we say contrast, that means bold. This kind of the index can be used as the the observation that we can differentiate the region with lower oxygenation level or with higher. So we say this is the contrast. This is the way that we can observe the difference in our brain. This term is actually delivered very early in 1990, actually. But now this is the main technique in the field of fMRI. I think over 90% study using the both fMRI. But actually there is another technique we called ASL fMRI. But I think that is a relatively small number of studies using this because the SNR is pretty low in ASL and there are several limitations in ASL anyway. So in this semester we focus on the both fMRI, not the ASL, arterial spin level fMRI. We are focusing on both fMRI. Okay, so I try to give you another pictures right there. Now we focus on the oxygenation level. So as you can see right here, you can see the neuronal activity. Once the neuronal activity happens right here, it definitely will increase the O2, the oxygen consumption or oxygen metabolism right here. So just like the index we introduced before, CMR2 will goes up, okay? But our body will compensate this kind of the events. Will definitely will give you sufficient blood flow. And you can see the plus sign right here. There is only one plus sign right here. It will cause one plus sign right here. But you will see the blood flow increment will have a 3 plus signs right here. The number right here means something. That means we will have a large amount, that larger than the increased amount of the CMR2. So your body will compensate, actually give you sufficient oxygenated. That means the hemoglobin with oxygen binding on it. Okay, so you can see it just increase a large amount of the oxygenated hemoglobin. And with the increment of the CMR2, definitely it will reduce the oxygenated hemoglobin, but again, in 1 unit. But with the sufficient blood flow, you can increase 3 units. It's just kind of a way to represent the difference between the compensation and the consumption right here. So for the net value or the total value right here, you can see the net effect that even you are in the neuroactivity state right here with a body compensation, actually the net effect is the increase of the oxygenation level in your blood, okay? So you can see there are two sides. We can say increase of the oxygenated hemoglobin. We can also say the fractional volume of the deoxygenated hemoglobin comes down. It's 2 things, okay? Hemoglobin either in the form of with oxygen or without oxygen. So this is 2 different forms. So once a part of this goes up, another one will just decrease or comes down, okay? So just remember this point that the neural activity will also give you a condition that increase of the oxygenation level right here. So we say these things is actually, you can use this term, is actually the mismatch between blood flow or blood supply and the O2 consumption. Okay, it's kind of a mismatch. Okay, so this is a result you should memorize. And now let's take a closer look about the hemoglobin. Since hemoglobin is one of the substances that can bring oxygen into your brain, we need to know these 2 essential forms of the hemoglobin. One is so-called oxygenated hemoglobin. That means this hemoglobin brings 1 unit of the oxygen. Okay, and there is another form we call the oxygenated hemoglobin. That means in the capillary pores or in the capillary space, that hemoglobin release the oxygen into to give the tissue the oxygen. So it will transfer from the oxygenated hemoglobin form into the deoxygenated hemoglobin. So normally we will say that when considering the brain, in the capillary space, before the capillary space, the hemoglobin may mostly are the oxygenated form. But after the capillary space, I mean, after the hemoglobin gives the nutrition, I mean the oxygen and the glucose away, then not glucose, sorry, just give the oxygen away, then the hemoglobin will mostly in the oxygenated form right here. Okay, but these two different forms, do they have the same magnetic property? I mean, do they have the same effects to the MRI? Actually, no. For the oxygenated hemoglobin, we say this is a substance of with the property of diamagnetic property. That means it will do very small distortion or do very small effect to the magnetic field, actually. So with or without the oxygenated hemoglobin, there is very limited changes in the MRI system. But for the oxygenated hemoglobin, this is something that has a property of the paramagnetic property. Para, that means it will change, or we say specifically, it will distort the surrounding magnetic field. So it can cause the changes in your brain or in the MRI environment. So actually, you can see if you have more oxygenated hemoglobin, there is no signal loss or signal changes in both fMRI. But if you have more the oxygenated hemoglobin, it will reduce the body signal because it will distort the surrounding magnetic field in the MRI. So it will cause the signal loss in your brain. However, we talked about that actually the neuronal activity, well, actually, we don't care about this one because it just causes limited effects on the magnetic field, right? So we only care about this one. You can see that once the neural activity happens, actually it's reduce the deoxygenated hemoglobin. Reduce the oxygenated hemoglobin means that you will have a higher body signal because the signal loss reduced because of the reduce of the deoxygenated hemoglobin right here. So this is actually kind of the reverse relationship. Because of the reduced interference in MRI, so we obtain the higher signal in MRI. So sometimes people get confused that always say, oh, you see the body signal comes up. That means because the oxygenation level is higher. But actually, it is because the amount of the deoxygenated hemoglobin comes down. So cause the signal increased. Okay. And to translate this kind of phenomenon in a more scientific way, we would say that actually deoxygenated hemoglobin can shorten the T2 relaxation time. Okay, this is kind of the way because shorter T2 relaxation time will cause more quick signal decay in MRI system. So actually, if you have less deoxygenated hemoglobin, it will cause less effect in reducing or in shorten the T2 relaxation time. So anyway, this page is actually presented for the people who have the MRI background. But for you, maybe just keep in mind that without the oxygenated hemoglobin, it will reduce the distortion of the magnetic field and hence increase the body signal level. Okay. So let's try to add in the time effects. That means that add in some temporal scenario into this kind of phenomenon. For example, now we can take 3 different time points right here. For time is equal to the 0. Right here, this is the first plot. And in the middle one is like 1 second. And this one is like the 6 second right here. As we mentioned before, that there is a time delay. There is a time delay after the neuronal activity that the vascular response will happen. There is a 1 to 2 second time delay, okay? So we take these 3 plots as the example. You can see the first one. If now it is the time 0, that means it's more like the resting period. That is more like the baseline. Your brain is doing nothing. So you can see this is a natural, the fraction of the red one is the oxygenated hemoglobin. The blue one is the deoxygenated hemoglobin. So you can see, maybe you can account that you have 1, 2, I think in this voxel, we take this square area right here to represent a voxel in your image. So we say, okay, within this image region, within this voxel region, we have 2 blue dots right here. That means we have 2 units of the oxygenated hemoglobin. And within this square area, we have 1, 2, 3, 3 red dots. So we say we have 3 units of the oxygenated hemoglobin right here. Okay. So when there is a brain activation or neural activity happens, just right after this 0 second, and after 1 second, you can see, oh, the blue dots increased. The number of the blue dots increased because between this 1 second, there is no blood supply that increased. It's just not that quick. So we can only see the CMR2, I mean the O2 consumption increased. So you can count that now we have 1, 2, 3, 4 blue dots, but only 1 oxygenated hemoglobin because maybe 2 of the oxygenated hemoglobin just released their oxygen to the brain tissue. So now they transfer into the oxygenated form right here. So as you can see right here, we say that if you have more the oxygenated hemoglobin, it will definitely cause the signal loss when you're using the bolus signal. So the signal level, you see, original one is 100, now it comes down to 99. It causes very small, very slight changes in the bolus signal, 99. But once the time comes to the 6 seconds, we say that normally the vascular response will cost 5 to 6 seconds to reach the peak value. I mean the highest vascular response right there. You can see lots of the oxygenated hemoglobin is flushing in. So now you can count so many oxygenated hemoglobin, the red dots right here, but a very small number of the oxygenated hemoglobin right here. It's just kind of the very sufficient or oversupplied idea about the increase of the blood flow. So now you can see since the oxygenated hemoglobin, the blue dots become so little, the signal will drive up, will become higher. So that is the scenario, that is a temporal scenario that you can imagine in your brain. So actually, when the neural activity happened, it will take 1 to 2 seconds to start increase the blood flow and start to increase the both signal in the fMRI. Okay. So I think I leave some words right here. If you want to read it, just read over this. Just what I'm talking about. So I'll try to give you a short summary that if you try to using some neuroimaging technique to probe the brain activation, actually there are several different ways you can do so. Okay, for example, you can try to probe the oxygen or oxygenation level. Okay, you can use both fMRI just like we described in the previous slides. There's another technique we called functional near-infrared spectroscopy. There's a more elegant way that actually you can resolve both, I mean the oxygenated hemoglobin and deoxygenated hemoglobin. For both fMRI, you can actually see the reverse relationship between the deoxygenated hemoglobin and the signal intensity. But actually, when you use the functional near-infrared spectroscopy, you can see both. You can actually measure the concentration of the oxy and deoxy hemoglobin, actually. And another technique is PET. I think this is an earlier technique. When fMRI is introduced, PET is an earlier technique. People can use the actually the radioligand or radio agent that you can inject into your body. But actually, there is specific nuclear that is called oxygen 15. We can use that to label the oxygen. Okay, so we can use this to probe the brain activation or investigate the brain activation. And there's another way that you can use MRI to observe the blood flow. That is the thing that we just mentioned, ASL, arterial spin labeling. But as I say, that the SNR for ASL is not quite good enough right now. So the majority of the fMRI study is using both signal. Final one is glucose. As we mentioned, that the energy is generated from oxygen and also the glucose. So you can also use the PET using the fluoro 18, so you can actually label the glucose. Or maybe there is a technique we call SEST. in MRI, you can actually use this. However, I think this one may have some issue about the temporal resolution. So I think the majority right now is using the board fMRI when you're considering the MRI technique. So I think I just leave the plot right here. It's pretty similar with the chart that I mentioned before, but I think it's particularly useful to you to understand that how we can use so many different biomarkers to probe the brain activation. Okay, so this is some waveforms for you to think about how the vascular response will happen after the neural activity right here. So you can see right here there is there is a literature published in 1999. Actually, you can measure the CBF, blood flow, CBV, blood volume, and also the bulk signal with your brain. So you can see in this gray period, actually this is a task period. You may ask a subject to do something. In this study, I think they ask the subject to do some finger tapping or something, just one of the motor tasks. So you can see during this area, we can take the body signal as an example. I think it is the white circular label right here, this one. So once the subject started doing the finger tapping, you can see increase of the body signal maybe around maybe 20% or something. I think this value is actually pretty high because normally we can only observe maybe 5 to 10% changes of the body signal. But in this paper, they can observe the 20% of the changes. But anyway, but also you can see the blood flow. You can see there is a very, very significant blood flow increment right here. And you can also see the value right here is a little bit different with the previous literature that I mentioned, that actually only 20% or maybe 7 to 8% changes right here. But in this paper, they observed 60% changes. I cannot say which one is true or not, but I can only say that in my experience, there's normally not that large change. Okay. And the final one is the blood volume right here. You can also see the changes right here. But the blood volume, you can see this is a less sensitive one. It's not as good as the body signal or blood flow. So I think right now blood volume is not one of the indicator or biomarker that we normally use to probe the brain activation. I think the body signal or blood flow are the better ones. Okay. So here is a summary flow chart right here. You can see once we deliver stimulus, for example, the visual stimulus, or we ask the subject to do the motor task, it definitely will induce the neuronal activity right here. Okay. So as we mentioned before, the neuronal activity based on the neurovascular coupling, it will induce a vascular response, or right here, the hemodynamic response right here. So the hemodynamic response will increase the blood flow and also increase the blood oxygenation level because more oxygenated hemoglobin comes into the brain region. And also definitely the blood volume because the flow increased. Okay. And finally, because of the nature about the oxygenated hemoglobin, once the reduction of the oxyhemoglobin happens, we can see increase of the body signal happens in the fMRI system. So this is a general scenario that why we can use the fMRI to probe brain activation. But again, it's highly dependent on the neurovascular coupling. So if there are any reason we'll break down this kind of coupling or at least change the coupling, you need to be very, very careful to give any inference using the fMRI. And this is a general protocol since we are going to visit our 3T MRI facility in this semester. I think I better to show you the protocol. Protocol that means the essential parameters that we normally use to perform an fMRI imaging. Okay, so normally we will use the gradient echo, this kind of the pulse that we use in MRI, gradient echo with EPI. EPI, the full name is the echoplanar imaging. It is the I think it is a fast imaging technique that can finish or acquire the whole data space or whole MRI data within one excitation. As I mentioned before, that we use RF pulse to excite the NMV, right? We can finish or acquire one imaging, one slice of your brain simply using one excitation. It is the, I can say it is the fastest image technique in MRI. So we use this because the hemodynamics, although it is slower compared to neuroactivity, but it's actually pretty quick changes in your brain because it only takes a few seconds, right? So with this kind of the techniques, I say the gradient echo EPI, we can actually image your brain. It takes, I think, only 2 seconds, around 2 seconds, maybe less, maybe more, but only 2 seconds. You can image in your brain once. I mean once. When you try to see the whole temporal pattern or whole temporal profiles of the both signal, you definitely need to repeatedly image your brain. Just like a video, you need to take photos repeatedly. And you just concatenate all the image together, it becomes the video. It's the same thing that if you want to have the both temporal profile, you need to repeatedly image your brain. So I say, with this gradient echo EPI, we can image our brain within 2 seconds. That means I can repeatedly image my brain with a 2-second interval. Okay, so if I want to really observe my brain activation through time, then 2 seconds, you can get the first picture. Then at the next 2 seconds, for example, this is a time 0, this is a time 2 seconds, this is a time 4 seconds, 6 seconds, 8 seconds, and so forth, so on, just with 2-second interval. That is the best thing we can do currently. Of course, there are some literatures using some kind of the time interval around 1.6 or something, but I think it's just pretty close to the 2 seconds. It's the normal setup that we use in fMRI. So we call the repetition time, that is the time interval between images slice to slice. We call the repetition time is around 2,000 milliseconds, that is 2 seconds. Okay. So there is some detailed parameters right here. You don't really need to know, but you should know the spatial resolution right here. For example, slice thickness is around 3.4 millimeter. It's actually pretty huge. It's actually pretty huge. And the matrix size, I mean the image size is around 64 by 64. Okay, so when considering the actual field of view you are using, about 220 millimeter square, actually each voxel is with this size, 3.44 by 3.44 by 3.40 millimeter cube. It's actually a pretty huge one. Compared to the anatomical MRI, it's actually a pretty huge one. But why we used this huge voxel in fMRI imaging? Because of the repetition time. If we try to give more smaller voxel, we'll spend more time in imaging, actually. So the repetition time may increase to 3 seconds or 4 seconds or maybe larger. But it will cause a very poor temporal resolution. Actually, the fMRI already has a poor resolution because we can only imaging the body signal in around 2 seconds, right? 2 seconds means that you can only have the 0.5 hertz frequency. This is pretty low, actually. So as I mentioned before, that within one voxel, there is actually contained over 1 million neurons inside. So do not give the inference that, oh, we can measure a single neuron activity. That is impossible in fMRI. That is crazy, okay? So actually, we are doing the repeatedly imaging using the fMRI, but for every single voxel right here, you can just plot the signal intensity changes along time. So again, the horizontal axis is the time with the 2-second interval. And the vertical axis represents the signal intensity. So as I mentioned before, if there is a brain activation happens, you may think that you can observe an increase of the body signal in a certain time point. Okay. So this is a general idea that I try to give you, that the protocol is more like this. But people may ask, then typically how long I need to ask my participant to stay in the MRI. I would say it highly depends on the experiment design. For the when considering the statistical power, I would say as long as possible. If you can give as many as the stimuli to the subject, you may have a very good statistical power. However, no one can do the as long as possible studies in your MRI scanner. In practical, normally 20 to 30 seconds is long enough to your participants, to your subjects. Over 1 hour, it's just an impossible mission. Over 2 hours, I know some studies deliver some kind of 2-hour fMRI study. That is crazy. I believe most of their participants is actually sleeping in the fMRI. I don't believe. Yeah. So here is the raw imaging. We will have more chance to see the imaging. So actually, this image is a little blurred. If you see other MRI imaging, you will see this image kind of has a very bad spatial resolution. Kind of blurred. You cannot see in detail. However, you still can see, for example, here is the lateral ventricle right here. You can see a little part of the third ventricle. You still can see some anatomical information. For example, you can definitely differentiate the cortex, the gray matter, from the white matter. However, the folding structure is not that clear. Okay, but this is what we have for the fMRI, for the EPI fMRI or both fMRI. So I think this is the final slide. I try to give you an example. This is from one of the study. Actually, the operator, the MRI operator, asked the participant to perform the finger tapping or something, or squeeze, hand squeezing. Just squeeze the subject's hand for 2 seconds. For 2 seconds. Okay. So each time when you see the red arrow right here, that means the operator indicated, maybe with the auditory instruction or through the visual instruction. Anyway, just instruct the subject to do the hand squeezing for 2 seconds, then release. So every single time you can see squeezing for 2 seconds, then release, and wait for another period, then do the hand squeezing again. So you will repeat it. Let's say maybe there are 20 events. I didn't really count this, but you can say maybe there are around 20 hand squeezing events right there. Of course, if you have more hand squeezing events, again, you may have a stronger statistical power to say, oh, I can observe an brain activation in the subject's brain. But you definitely need to consider the time. You can see right here, the overall duration for this experiment is maybe around 300 seconds. It's just around 5 minutes, right? But you need to understand that for the fMRI study, not only this sequence is demanded for the imaging, you also need to do the high resolution anatomical imaging, and maybe different conditions for the fMRI, and maybe you want to add in some diffusion tensor imaging or something. So normally you need to control the overall scanning time within, I think, at most within 1 hour, I think. And now you can do one thing, that you can just crop your signal. You use the red arrow as the original point. Each red arrow as the original point. You can just crop the signal, and you realign all the signals into this kind of form. We call block average, or just overlay all the signals with the original as the red arrow indicates right here. So you can now observe whether over these 20 different events, whether the signal profile is similar with each other. You can do the average, we call the block average or something. You can average the signal across events, so you can obtain a more confident or stronger signal, represent the brain activation or both signal reflecting the hand squeezing task. Okay. So this is a general idea that we can obtain the imaging and transfer the imaging to the both signal, and we can have the average profiles that across different events right here. Okay. So I think today I spent 2 hours, one for physiology behind the fMRI, another one is a general idea what is the resource of the fMRI, the oxygenated hemoglobin. So I think once you know the physiology behind this and you know how fMRI works, I think it will definitely help you to understand why some kind of the, for example, pre-processing steps is demanded for fMRI. Why some kinds of fMRI analysis is not always suitable for every fMRI data. There is some particular reason behind this. I will go through different techniques in this semester, but I think this week is particularly important. So if you cannot catch up, please go back home and just see the videos again.